9.2 Air Standard Otto Cycle Analysis. The air standard Otto cycle is modeled as a closed system. We neglect the changes in kinetic and potential energies. Using the energy balance equations, we got the following work and heat transfer relations in each process. W12 is the work done on air. It is the specific internal energy difference between state 2 and 1. Q23 is the heat transfer to air. It is the specific internal energy difference between state 3 and 2. W34 is the work done by air. It is the specific internal energy difference between state 3 and 4. Q41 is the heat transfer from air. It is the specific internal energy difference between state 4 and 1. So net work of the cycle is work produced minus work consumed. So this is U3 minus U4, U2 minus U1. Or the net work of the cycle can be expressed as the net heat added to the system. Both gives us the same result. The thermal efficiency is the ratio of the net work of the cycle to the heat added. It is expressed in terms of the specific internal energy in 4 states of the cycle. We define the compression ratio R, which is V1 over V2, or V4 over V3. See the PV diagram. The volume here is V1, V4. So V1 equals V4. Volume here is V2, V3. V2 equals V3. So V1 over V2 equals V4 over V3. So the compression ratio R is the ratio of the largest to the smallest volume. The efficiency of the air standard Otto cycle is a function of the compression ratio only. So the efficiency of the Otto cycles increases with the increases compression ratio. Recall that we define the relative pressure and the relative specific volume for air under isentropic processes. The relative volume at state 2 can be expressed in terms of the relative volume. The relative specific volume ratio equals V2 over V1, the volume ratio. So the equation can be solved for VR2, and the V2 over V1 is the inverse of R, compression ratio. VR4 can be also expressed in terms of compression ratio R. So we will use these relations to determine the unknown properties during the isentropic processes. Example 9.1. The temperature at the beginning of the compression process of an air standard Otto cycle with a compression ratio of 8 is 540 degree Rankine. The pressure is 1 atm and the cylinder volume is 0.02 cubic feet. The maximum temperature during the cycle is 3600 degree Rankine. Determine the temperature and pressure at the end of each process of the cycle. The thermal efficiency, the mean effective pressure in atm. So this is an air standard Otto cycle. The piston cylinder system contains air, which is considered as an ideal gas in a closed system. We'll neglect the changes in kinetic and potential energy of the system and the Otto cycle consists of 4 reversible cycles, 2 constant volume processes, and 2 isentropic processes. I'm going to begin with creating a table with properties in each state. So we have 4 different states: pressure in atm, temperature in degree Rankine, volume in cubic feet, specific internal energy in BTU per pound. This table will help us to organize the data and clearly shows what properties are known and what informations are missing. The main objective of analyzing the Otto cycle is to determine the thermal efficiency. Thermal efficiency is expressed in terms of internal energy. So I've added a column for internal energy at each state. Let's begin with state 1. At state 1, the temperature and pressure are given in the problem statement. So we can fix the state. Temperature 540 degree Rankine and pressure 1 atm. And volume is also given 0.02 cubic feet. So see table A22, ideal gas properties of air. At state 1, temperature is 540 degree Rankine. Internal energy U1 is here, 92.04. And state 2, we don't know much about state 2. The compression ratio R is given, so compression ratio V1 over V2 is given. It is 8. So V2 is V1 over 8. V1 is 0.02. So V2 is 0.0025 cubic feet. Going from state 1 to state 2 is an isentropic process. For air under isentropic process, we can use the relative volume as we know the compression ratio. The compression ratio R equals V1 over V2. And this is equal to VR1 over VR2. The relative pressure ratio. And we can write it for VR2. So V2 over V1 times VR1. So V2 over V1 is 1 over R. And VR1, the relative pressure at state 1. VR1 is here. So 1 over R times 144 times 32. So we got VR2. So from the table, by interpolating with VR2, which is 18.04, falls between these two numbers. So T2 is 1212 degree Rankine. U2 is 211.3 BTU per pound. To summarize what we did from temperature 1, so we got relative pressure VR1. From VR1 we got VR2, and from VR2 we got temperature and internal energy at state 2. Mass remain constant throughout the processes using the ideal gas law. PV equals MRT. Mass at state 1 equals mass at state 2. So we can write P1 V1 over RT1 equals P2 V2 over RT2. R cancels out and we can solve it for P2. So P1 V1 over V2 T2 over T1. P1 is 1 atm. V1 over V2 is compression ratio. T2 1212 degree Rankine. T1 is 540. So P2 is 17.96 atm. 17.96. We can also determine P3 with ideal gas law. So during process 2-3, mass remain constant. So we can write, and process 2-3 is a constant volume process. So V2 equals V3. And R cancels out. So P3 is P2, T3 over T2. And temperature at state 3 is given, 3600 degree Rankine. So P3 is 53.3 atm. See table A22E. At 3600 degree Rankine, internal energy U3 is here. And V2 equals V3. At state 4, we use the relative volume again, as process 3-4 is an isentropic process. So the relative pressure ratio, VR4 over VR3 equals V4 over V3. VR4, VR3 times V4 over V3. V4 over V3 is the compression ratio. VR3 is the relative volume at state 3. So at 3600 degree Rankine, this is VR3. So 0.6449 times 8. So VR4 is 5.16. So in table A22E, VR4 is 5.16, which sit between these two numbers. So the temperature is between these two, and the internal energy is between these two. So we can determine the temperature and the internal energy at stage 4. So do the interpolation, and temperature 1878. Internal energy 342.2. And V1 equals V4. So volume at state 4 is 0.02 cubic feet. Again, we are going to use the ideal gas law. So M4 equals M1. Using the ideal gas law, we can write P4 V4 over R T4 equals R cancels out. Process 4-1 is a constant volume process. V4 equals V1. So we can determine P4. So pressure is 3.48 atm. So we completed the tables. Now let's determine the unknown quantities. First, the thermal efficiency of the Otto cycle. Thermal efficiency is expressed. We know the specific internal energy at each state. Put the values in. The thermal efficiency of the Otto cycle is 51%. Determine the mean effective pressure in atm. The mean effective pressure is defined as the net work divided by the displacement volume. Maximum volume minus the minimum volume. So we know the volume V1 and V2. And net work, we know the internal energy at each state. We just need to calculate the mass of air. use the ideal gas law. So we can solve it for the state 1, P1, V1, T1. So now we can calculate the net work. So the mean effective pressure is calculated. 118 psi or 8.03 atm. The higher the mean effective pressure, the greater net work it produces. The MEP value is useful to compare the performance of internal combustion engines of the same size.